I'm Professor Rad, and this is Precalc video 116, writing in Vertex form. In our previous video, we talked about the vertex form of a quadratic function, and we can pull all sorts of good information just from that form of the function. So in this video, we're going to talk about what if I have a quadratic function given to us in standard form, how do I turn that into vertex form? So to do this, we're going to use a technique called completing the square. So I want to talk about what that is real briefly before we go through and to do an example of using it. So if you have a quadratic function, a perfect square, so if you have something like x plus 3 quantities squared, remember that you can't distribute exponents over addition, right? So if I was going to find this and expand it out, I would think of it as x plus 3 times x plus 3. And then if you're familiar with foiling, you would FOIL this, or you would distribute this out. I like to think of it as like shaking hands. Everybody in here shakes hands with everybody over here, right? But when you multiply this all out and you simplify it, you're going to end up getting x squared plus 6x plus 9. Now, it doesn't matter, well, let's break this down a little bit before I get into that. So what I'm going to do is I'm going to rewrite this end result in terms of only things that we had to start out with, as much as possible, I guess. So for instance, we started out with something that had a 3 in it, and I noticed that both 6 and 9 are multiples of 3. 6 is twice 3, and 9 is the square of 3. So I can rewrite this as x squared plus 2 times 3x plus 3 squared. Okay. Now, it turns out that it doesn't really matter that this was 3. If this had been 4 instead, and I multiplied this all out, I would have x plus 4 times x plus 4. And I would have gotten an 8 here, and then a 16. And what's cool about this is that 8 is the same as 2 times 4, and 16 is the same as 4 squared. Similarly, if I had like a 5 here, then this would be a 5, and that would be a 5. And if I multiplied it all out, I would get a 10 here, and I would get a 25. Which means 10 is the same as 2 times 5, and 25 is the same as 5 squared. So all perfect squares, so all binomials, when you square them, have this format that if you have x plus something squared, I'm just going to call it a, that's going to give you x squared plus 2ax plus a squared. So they're all going to have that same format. So when we go to complete a square, we're going to take something that looks like it's in standard form, so it's going to be expanded like this. And we're going to try and figure out how can we add an appropriate amount to that to be able to factor it so we get a perfect square here. And the key is going to be in this middle term. Notice how in this middle term, we have 2a as our coefficient, and this a harkens back to what we had originally. So what I want you to keep in mind is that the coefficient of the linear term is twice what we have here in our perfect square. So the easiest way to kind of see what a perfect square is, completing the squares like, is to work through an example. So we're going to do like the worst kind of example, a complicated example, so you can kind of see all the mess to begin with, and we'll walk through it and come back to this idea towards the end of the example. All right, so here we go. So for this example, we're going to rewrite this quadratic, which has been given to us in standard form. We're going to write it so that it's in vertex form by completing the square. So the first thing I'm going to do is rewrite my function. So I've got negative 2x squared plus 8x minus 11. Now, to help me complete the square, I'm going to take anything that has a variable and kind of separate it from anything that doesn't have a variable beside it. So that means I'm going to take the negative 2x squared plus 8x and keep that all close together. And then the minus 11, I'm going to go send off by itself. Ultimately, this piece here is what we're going to try and turn into this piece here of vertex form. And then this constant term, there's going to be more over here, but that's what's going to turn into the k. So eventually, that's kind of the two pieces that we're trying to get to here. The next thing we're going to do, because we're in vertex form, we have just an x minus h. We want to try and get a coefficient of x squared that's just 1. So we're going to factor out what will become the a value. So just from these components that have the x, whatever the coefficient of x squared is, you're going to factor out. So it doesn't matter if this number divides this one or not. Whatever number this is, we're factoring it out of there. So we're going to factor out a negative 2, and that gives me x squared minus 4x. I'm going to give myself a little bit more space here, and I'm going to bring down this minus 11. I'm not factoring out the negative 2 from the negative 11 because this negative 11 is a separate component. Okay, so I don't want this to mix with the x's anymore. Okay, now this is where that like 2a piece is going to come into play. So when we had this, is going to equal x squared plus 2a x plus a squared. This is kind of like what we're looking at beforehand. So in order for us to figure out what this a is, we're going to have to take half of the coefficient of the x term. So I'm going to take half of this coefficient. I'm going to divide that by 2, and I'm going to get negative 2. In order to get a perfect square, I have to be adding a squared. That's how I'm going to get this format. So I want to take that negative 2 and square it so that I get this now perfect square format that we had over here. So that's kind of what we're trying to achieve, so that this piece that's in the parentheses will factor into x minus 2 quantity squared. That's what all this work is. So this is called completing the square because we need to find the piece that will complete this expression and make it into a perfect square. It's kind of where all the background work is in this whole process, why we're doing this. Now, you know that you can't just add things to something and say, oh, it's all equal. No, you have to maintain balance. And if you've used completing the square in the past, you may have done that by adding the same amount to both sides of an equal sign. The problem is here, we don't have both sides of an equal sign. We have an expression that we are manipulating. And that's going to be the case in calculus as well. There will be times where you have a function and you have to work within the expression. You don't have two sides of an equation to balance. However, I do know if I add an amount and I subtract the same amount, I'm staying balanced. I'm not having, there's no problem with that. So if I add this plus negative 2 squared, then I can subtract that negative 2 squared and maintain balance, right? So we've got our minus 2 squared plus a negative 2 squared. And now we're going to subtract that negative 2 squared to get 0, right? Almost, we're so close. So the problem is this negative 2 being squared is inside parentheses. And there's a coefficient in front of those parentheses. So we're not really adding negative 2 quantity squared. We're adding negative 2 quantity squared times negative 2. So we want to subtract negative 2 quantity squared times negative 2. All right, so we do this process. We're going to bring this negative 2 down. This whole piece factors into this perfect square. And then I'm going to bring down these pieces. I'm going to simplify a little bit. So I bring down my minus 11. Negative 2 squared is a positive 4 times a negative 2 is a negative 8 times a negative is going to be a positive 8. And then I can combine these like terms. To get negative 2 times x minus 2 quantity squared minus 3. All right, so that is how we can write a function in vertex form by completing the square. Now, if you really wanted to, you could take your general standard form, ax squared plus bx plus c, and complete the square on that. So you'll be having a's, b's, and c's in that mess. And that will get you a general formula for the value of h and for the value of k. So I'm going to leave that kind of as like an exercise if you want to try practicing that out. Maybe we'll see it on a lab in the future. I don't know. But for right now, I'm just going to spill the beans and tell you what those formulas are right away. So if you were to complete the square on the general standard form here, ax squared plus bx plus c, you would get a result that shows that h is the same as negative b over 2a, and k, which is the same as f of h, because our vertex has the coordinates hk. So that would be one way to find it. Or you could find it in terms of a, b, and c as c minus b squared all over 4a. Well, not all over 4a, it's just b squared over 4a. I misspoke. So you can use these formulas to take a function that's in standard form and put it into vertex form as well. So for instance, let's redo the last example using these formulas this time. So we had, check in my notes here, we had negative 2x squared plus 8x minus 11. So let's put this again into vertex form, but this time instead of completing the square, we're going to use these formulas here. So first I'm going to find h. So h is negative b over 2a. So a is negative 2. B is 8. And c is negative 11. So negative b is going to be negative 8 over 2 times a. A is negative 2. So we get negative 8. 2 times negative 2 is a negative 4. And that will give us 2. For k, it's up to you which formula you personally prefer. I'm not going to require you to use this one or that one. I might just say use the formula, use a formula to find the vertex. So this is our formula for h, that's what we'll use. To find k, if you prefer to use a, b, and c, go ahead and use this one. I have trouble memorizing stuff, so I know that k is the y value when the x value is h. So since we already went through the trouble of finding h, I'm just going to throw that into my original function, and that will tell me k. So I can do negative 2 times 2 squared I'm getting 2 from H. So -2 times 2 squared plus 8 times 2 minus 11. Let's see, 2 squared is 4 times -2 is a -8. 8 times 2 is 16 minus 11. So -8 plus 16 is going to give me an 8, and 8 minus 11 is a -3. So this gives me my H and my K. So we can now substitute those into this formula. So y equals a x minus h, so -2 plus k, so in this case, -3. And I have really good news for us. The good news is that the a in the vertex form is the same as the a in the standard form. So a here was -2. So we have a -2. And there we go. That's how we can use the formulas to write a function in vertex form. And let me see, I'm going to just check. That is what I have written down for the previous example as well. So looks like it worked out. Let's do another example of using these formulas, this time applying them to a word problem, everyone's favorite part of math, right? For this example, we're going to be a company that sells boxes of candy. So a company finds that the revenue generated by selling X boxes of candy is given by this function R of X, which is 9.5x minus 0.04x squared. Then we really have like 3 questions. Can you maximize the revenue? And if so, what is the maximum revenue? And how many boxes of candy must be sold in order to maximize the revenue? So this is a very short question if we can't maximize the revenue. So I'm going to guess we can for this one, but let's see why. Mathematically, we'll be able to do that. So this is a quadratic function. So when you have a quadratic function, there are one of 2 graphs that can happen, right? We can have a smiling parabola, or we can have a frowning parabola. If I'm trying to maximize revenue, then I want to have a situation where my parabola is frowning, because that turning point is going to be where my maximum is. Excuse me. Otherwise, if I have just the smiling parabola, then it's just going to continue forever on both sides, and there won't be a maximum. There will be a minimum, but not a max. So in order to determine whether or not our parabola is smiley or frowny, we can look at the value for A. And remember that the value for A, whether we're in vertex or standard form, is the same value. So if I look at our function here, we got to be a little careful because it's not perfectly in standard form, because the x squared term came second. So A in this problem is going to be -0.04. So that means since A is negative, we're going to be a frowning parabola. So we're going to look like this. So this answer to can you maximize the revenue is yes. So for this question, I'm going to try and write it over here. My answer would be yes, because A is a -0.04 is less than 0. So the parabola opens downward. And the vertex is the maximum. All right, so the first part of this question is done. We can maximize this function because it's opening downwards, and we know that the maximum will be achieved at the vertex. So the rest of this question is asking us what is the maximum revenue and how many boxes of candy must be sold in order to do that. So the max revenue is going to be the y value, because remember our maxima and minima are the y values of the points. So the maximum revenue is going to be the y value of the vertex, in other words, k. And the number of boxes of candy that we're going to need to sell in order to achieve that, that's going to be our x value of the vertex. So that's going to be h. So since we need to find both of them, we're going to be using both of these formulas here, where h is negative b over 2a, and k is f of h, or if you prefer, c minus b squared over 4a. So since we have to find both, I'm going to find h first, and then I'm going to plug it into the function to find k. So h is negative b over 2a. We already know that this is our value for a. And because this is the coefficient of x, that's going to be b. So we have negative 9.5 over 2 times a negative 0.04. I was getting nervous with this value being a negative because I was like, we can't have negative boxes of candy that we're selling, because that would mean we're buying all the boxes, but we're good to go. And now, because in applications, numbers tend to be messier, we're just going to calculate this on our calculator. So 9.5, negative 9.5, divided by 2 times negative 0.04. I'm going to make sure to put parentheses around that 2 times negative 0.04 when I throw this in the calculator. Oh gosh, I don't know if can you see that? Hopefully you can, so that the order of operations are followed. And that's going to give me 118.75. So this is going to be where my the number of boxes that I'm going to need to sell. Now we're going to assume we can sell 3/4 of a box. Sorry, 118.75. If I was only selling whole boxes of candy, then I would need to look at the two numbers of boxes surrounding this. In this case, probably 119 would work better, but I would check out 118 and 119 and see what the corresponding y value is when I substitute those into the function to get the maximum revenue. But we're going to assume we can sell 3/4 of a box. These are bigger boxes, so we can sell, partial boxes. So to find k, we're just going to throw that into the function. So k is going to be f of 118.75. That was the value we found for h. And I'm just going to throw that into the formula. Oh, I guess this should be r of that instead of f. So this will give us 9.5 times 118.75 minus 0.04 times 118.75 squared. And this time for sure, I'm going to want my calculator to help me here. So 9.5 times 118.75 minus 0.04 times 118.75 squared. And let's round this to the nearest cent, just to keep it okay in terms of monies. So this is going to be 564.06. So our maximum revenue that we can achieve is $564.06, and then some partial cents if we wanted to be really particular about it. And then we would have to sell 118 3/4 of a box to get there. So that's it for this video. So we've looked at both how we can write a function to be in a quadratic function to be in vertex form. And we've also, from that, we know it's possible to derive these formulas so that we can apply them to situations like this one, because this would be a beast to try and complete the square on, right? Yeah. All right, so in our next video, we're going to apply all of these techniques to, here's the graph of a quadratic. Now let's write a function for it. Let's write the equation for it. So I hope you found this video at least a little bit helpful, and I hope you have a wonderful day. Bye for now.